We're going to tackle another application of integration in this video, and that is of finding expected value and some statistics for a probability density function. So we're going to go back to the rolling a six-sided die 100 times, this discrete example, to then hopefully help us determine how to do this for a continuous variable. And so again, we have a discrete variable because we have very distinct outcomes, 1, 2, 3, 4, 5, 6, and we can't have anything in between. So they're separate, they're discrete, and we had their frequencies as are listed in this table, and from that we can compute the probability of each outcome, right? Whatever variable values it can take on. The variable is the number of dots on the die, and so it can take on values of 1, 2, 3, 4, 5, and 6, and we can compute those probabilities, which we did in a previous video. So how do we use that to come up with, well, let's say I wanted to do this experiment another 100 times. What number of dots can I expect on average to get on a roll? Okay. So based on this information, our table that has these outcomes and probabilities, how many dots on average might I expect to get if I rolled another 100 times? This is actually quite an easy computation to do, if not a little bit tedious, is we basically take the number of dots and we multiply by the probability of getting that number of dots. And I do this for each of my possible outcomes and I add that all up. So I'm essentially taking 1 dot times a probability of 0.18 plus 2 dots times a probability of 0.2 plus 3 dots times a probability of 0.12 plus 4 dots times a probability of 0.13 plus 5 dots with a probability of 0.21 plus 6 dots times a probability of 0.16. And if we plug this into our calculators, we get 3.47. So on average, I'm getting somewhere between 3 and 4 dots on 100 rolls, right? An average of about 3.5 dots, right? Well, we can't actually get 3.5 dots, so I'm going to get either 3 or 4 in general, okay? That's my average number of dots rolled if I roll this about 100 times. Again, that's right, I can't get 3.5, and this is for a discrete, but what if we want a continuous variable? Again, things like heights, times, volumes, those sorts of things, distances. So let me roll back and let's review again how I did this, right? I took the value of the variable, all the possible different values the variable may take on, a 1, a 2, a 3, a 4, a 5, or a 6. And then I multiplied each of those by their respective probabilities. Okay. So in shorthand notation, this is the sum, so that capital sigma means the sum of x times y, right? If I plotted these on a graph, plotted these as dots, we basically are just taking the x value times its y value. Another name for that y value is the probability, p of x, right? Now when we have a continuous function, we don't have points like we do for a discrete function. We have an entire curve, right? And so there we have an infinite number of points that make up that probability density function. So I can't use just a sum. I'd have an infinite sum. Well, I guess we can. There's a way mathematically to do that. But we have some tools at our disposal. And so what do those tools look like? Well, our expected or mean value, we determined when we had a discrete probability, a discrete distribution, a discrete variable was the x variable times the probability of getting that x variable, right? So 1 times the probability of rolling a 1, a 2 times the probability of rolling a 2. So however many values I have, in my previous example, n was 6, but I could have 10, 12, 20, whatever. And as n gets larger and larger, as we go toward infinity, we're going more toward a continuous function because we're getting an infinite number of values in between all these possible ones, right? And then we've got an infinite number of y values that correspond to those values. And so if I try to do x times y, well, I have an infinite number of those. When we saw about computing areas, one way to tackle that is by using the definite integral. So if I wanted to figure out the mean or expected value for whatever variable this is, a continuous variable, it's similar to the average value, but not quite the same, okay? So basically, if we want to compute that value, I'm going to use that same idea. I'm going to take x times the probability and do an infinite sum. Well, we use a definite integral to compute this infinite sum. And so we basically take that x times now the probability density function. Rather than individual probabilities, I have a function that's represented by that. And so we can use that to compute what is called the expected value or mean of this probability density function. Now you might have seen, right, like a normal curve, right? Here's our normal curve. And on a normal curve, the mean is right here in the center. Well, if we have a skewed distribution like I have here, or not bell-shaped, well, then the mean is not quite right in the middle. It's going to be maybe someplace over here, right? That's going to be where the mean is. And so the way that we compute that is by computing x times the probability density function, that definite integral. So let's take a look at an example. So here we're given a probability density function of f of x equal to 1/2 x minus 2, and it's over the interval from 4 to 6. Remember, the total area has to be equal to 1, so that's why we're only looking at it between 4 and 6, because that'll give us the total area. Find e of x, the expected value. They could have also asked for the mean, find the mean of this probability density function, or mu, that is the Greek letter, lowercase mu. And so we said in the previous page, the way that we do this is we take the interval and we take x times the probability density function. We compute that definite integral. And so in this case, a is 4, b is 6, and then x times 1/2 x minus 2 dx. So first off, I'm going to distribute that x. So this will be 1/2 x squared minus 2x. And I can do that because there's no exponent up here, right? I can do that. There's no exponent. I can distribute that x as long as there's no exponent on those parentheses. And so now it's just a matter of finding my antiderivative. So 1/2 times 1/3 x cubed minus 2 times 1/2 x squared. And then I need to compute that from 4 to 6. So this will be what? 1/6 x cubed minus x squared from 4 to 6. So I'm going to plug in 6 and then plug in 4 and subtract. So when I plug in 6, I get 0. And when I plug in 4, I get negative 5 1/3. So 0 minus a negative 5 1/3 is a 5 1/3. So this is my expected value for this probability density function. And it makes sense. It should fall somewhere between 4 and 6, right? And because that's the values, it can only take on values between 4 and 6. Whatever this random variable, continuous random variable is, can only take on values between 4 and 6. So my expected value or mean or mu, the population mean, is 5 1/3. Okay. Now, we can also use our probability density function to compute a variance and standard deviation for this collection of data. So we know we can compute e of x, which is the mean, otherwise known as mu. Then if we replace x with x squared, then basically we replace that x with an x squared there. And that gives us something called e of x squared. Now notice only that part gets replaced with x squared, not there. We don't replace x with x squared in the probability density function, just the out front. we can compute the variance, which we use the lowercase Greek letter sigma and square it. So variance is sigma squared. Turns out that is computed by finding e of x squared and subtracting off the quantity we get for e of x squared. Or in other words, e of x squared minus the mean squared. That's how we compute the variance. Standard deviation, that's simpler. That's just the square root of the variance. And so that's just sigma without the square on it. Okay? So we want to keep that in mind. So let's do a problem. Given the probability density function f of x equals 1/4 x over the interval from 1 to 3, find e of x squared, the mean, variance, and standard deviation. So this probability distribution function, right, the continuous random variable can only take on values between 1 and 3, so I want to keep that in mind for the mean. My mean better be between 1 and 3, and this is the shape of its distribution of values, 1/4 x. All right, so it asks us to find e of x squared, the mean, variance, and standard deviation. Great, so let's go down the list. E of x, we're using that formula, is use the interval that's given, and x times the probability distribution function. So in this case, that's from 1 to 3 of x times 1/4 x dx. Or in other words, this is from 1 to 3 of 1/4 x squared. So doing my integration, this is 1/4 times 1/3 x cubed from 1 to 3. And so if I substitute 3 into that and 1 into that, I get, plugging in 3, I get 27/12. Plugging in 1, I get 1/12. So when I subtract, I get 26/12, or in lowest terms, 13/6, which is equivalent to 2 1/6. Okay? So then I need to compute e of x squared. So again, this is from 1 to 3, and I replace x with x squared times 1/4 x dx. This gets us the integral from 1 to 3 of 1/4 x cubed dx. So I need to do that computation. So 1/4 antiderivative of x cubed is 1/4 x to the 4th, and again from 1 until 3. And I end up with 81/16 minus 1/16 gives me 80/16, which is equal to 5. So far I have e of x, and I have e of x squared. Now I need to find the mean, variance, and standard deviation. Now remember, the mean is the same as what? E of x. So that's our 2 1/6, or our 13/6. The variance is, remember, e of x squared minus the mean squared. So this is going to be e of x squared, which is 5, right? E of x squared is 5 minus the mean squared. So I'm going to use the 13/6 squared. So this will be 5 minus 169/36, which is 11/36. Okay, so that's the variance. So that's our next result, our variance. And then remember, standard deviation is just the square root of the variance. And so the square root of 11/36, square root of 36 is 6, so we can simplify this to square root of 11 over 6. And so that is our last result. Okay. So e of x was 2 1/6, or 13/6, however you want to write that. E of x squared was 5. That means the mean is 2 1/6. The variance is 11/36, and the standard deviation is square root of 11 over 6.